Hi, good day. Welcome to our webinar series for the 3D CT X-ray or 3D computed tomography X-ray on non-destructive testing or NDT with digital radiography and 3D computed tomography using industrial X-ray. This is brought to you by Advanced Device and Materials Testing Laboratory or ADMATEL under the Department of Science and Technology with ITDI Industrial Technology Development Institute. Our speakers composed of the Physical and Metallurgical Laboratory team. First is Ms. Angeline Alcain. Next is John Kenneth Valerio. Next is Engineer Aldrin Jan Tabuso. And yours truly, BJ Salon. So the topics that we will discuss today is about the history, the principles of X-ray, radiography setup, what is digital radiography, what is computed tomography, and our X-ray services and our capabilities. Also, we have a bonus content. It is the CT Auto Run tutorial.
Before we go further, let me discuss to you the brief history of X-ray, how it is discovered, and its development up to the computed tomography or CT. Wilhelm Röntgen, a German mechanical engineer, discovered the X-ray in 1895. While working with cathode ray tube, he applied it with high voltage. He observed that it produced fluorescent glow. When Röntgen shielded the tube with heavy black paper, he discovered a green fluorescent light emitted from the tube. He found this a new type of ray could pass through a human tissue but not in bones and metals. Röntgen developed a setup called Röntgenogram to study this unknown ray, therefore it is called X-ray. His first experiment was a film of hand of his wife Anna Bertha Ludwig. From 1895, when Röntgen discovered the X-ray, it is then used by battlefield physicians to locate bullets in 1896. And so, in 1912, X-ray were mostly used in medicine and dentistry. Development of cathode ray tubes was made over the years, giving us high-resolution images for more conclusive results and more applications. In order X-ray to be used for industrial purposes, higher voltage are required to produce a ray with satisfactory penetrating power, so higher vacuum tubes were developed from then. Up to 1972, Godfrey Hounsfield, an English electrical engineer, introduced computed tomography at the British Institute of Radiology in their annual conference, opened up the use of X-ray into a wider range of applications and capabilities, not only for medicine, but also for industrial applications.
Principles of X-ray. What are X-rays? X-rays are high-energy electromagnetic radiation which has a shorter wavelength than light. It's around 0.01 nanometer to 10 nanometer. It can penetrate through solids and ionizing gases. There are two types characterized as soft and hard X-ray. Soft X-rays are defined with a wavelength in 0.1 to 10 nanometers at 0.1 to 5 keV. It can easily absorb by air, while hard X-rays are defined in terms of wavelengths below 0.2 nanometers at 5 to 10 keV. This type of X-ray is widely used to image the insides of visually opaque objects, Thus, it has a high penetrating ability. In terms of this, the KeV value is the power or energy required to penetrate an object. So how do we produce X-ray? X-ray can be generated by a vacuum tube that uses a high voltage between two electrodes to accelerate the electrons released to a high velocity aimed at a metal target. This is usually tungsten or another heavy metal. Upon striking the target, the accelerated electrons are abruptly stopped, which generate a Bremsstrahlung or braking radiation. The deceleration of electrons produce an electromagnetic radiation and heat. Typically, gamma rays are produced using protons. Most energy is turned into heat. Less than 1% turns into X-ray radiation. There are three main classifications of X-ray sources: the natural source, the artificial source, and the specialized source. Natural source, which is naturally produced by a radioactive elements such as radon gas, cosmic rays, UV light. Artificial source produced using high voltage electron tubes, while specialized sources, which uses particle accelerator generating synchrotron radiation. For radiographic tests, artificial sources are commonly used for safety purposes. Once the voltage is cut off, the source stops producing radiation. The voltage could also be adjusted, which affects the quality of X-ray radiation for certain applications. There are two types of X-ray tube: the sealed-off tube or the closed-type tube, and the open-type tube. In terms of the sealed-off tube must be in constant vacuum. It has a high image repeatability with no need of maintenance, has a fixed magnification. However, the lifespan is determined by the lifespan of the filament. The second type of tube is called an open tube. The open tube must be vacuumed before using. This is good for magnification for failure analysis. It requires periodic maintenance. The filament and other parts are easily replaceable and has a longer lifespan relatively.
Now, we will be talking about a common setup used for radiography. As you can see in the image, this is the first ever radiography setup made by Wilhelm Röntgen, which is referred as the Röntgenogram. But first, what is radiography? Radiography is the practice of imaging with the use of radiation. It has three major requirements: the X-ray source, the sample, and the X-ray receiver. In the diagram shown, the X-ray source, commonly a vacuum tube, will produce the X-rays, which will then penetrate through the sample. The penetrating X-rays, also referred as signals, will be received by either a photosensitive film or an X-ray detector. Photosensitive films were widely used for radiography, but the development of X-ray detectors gave way to digital radiography is a two-dimensional X-ray inspection technique. It uses digital X-ray detectors in place of X-ray films, also known as the photosensitive films. It also allows real-time inspection, and at the same time, the radiographs can be manipulated and enhanced quickly and easily using the software. So in the images below, we can see here the source, the sample, and the detector. And the image in the right shows the radiograph of an external hard drive. So for digital radiography, the radiographs or the samples can be magnified in two ways, either in geometric magnification or in digital magnification. Geometric magnification is simply the magnification of the sample as a result of its physical position between the X-ray source and the X-ray detector. So the magnification of the object increases as the ratio of the source object distance to the source detector distance increases. This magnification is quantified with the use of this equation: m is equal to d1 over d2, where m is the magnification, d1 is the distance between the source and the detector, while d2 is the distance between the source and the object. The image to the right is also representing this magnification and this equation. So as you can see here, d1, or the distance between the source and the detector, was remained constant for these three images. Meanwhile, d2, or the distance between the source and the object, varies from image to image. So we can see here that as the object is placed nearer to the X-ray source and farther away from the detector, the magnification is increased. So this magnification would be favorable for some applications. However, this would also only capture a small part of the sample for the radiograph. Now, digital magnification is another type of magnification which is now done to the radiograph using a software. So this means that there's already a radiograph captured, and then we will just be using an external software that is capable for such magnifications. So the quality of the magnification highly relies to the resolution of the image. So this resolution is expressed in pixels. So pixels stands for picture element. So it is the smallest controllable element of a picture represented on a screen. And as the sample images suggests, if the resolution of the image is low, when it is magnified, the image could be pixelated, as you can see here. So if we are to conduct digital magnification, we should be sure that the resolution of the actual image is good enough. So here are some advantages and disadvantages of digital radiography. So first advantage is that it can capture images relatively faster than the use of photosensitive films. There is also an ease of viewing, editing, and deletion compared to the use of film radiographs. So since everything is done digitally with the help of softwares and computers, it can be easily viewed, edited, or deleted. So also it is applicable for bulk scanning. It depends on the setup of the samples in the X-ray machine. So for some disadvantages, the images are projections in one direction only, or in one orientation of the sample, which means that if some of the components of the object overlaps each other, it may erase some details or make some parts blurry. So this means that the image must be oriented properly with respect to what we have to investigate in the sample. In ADMATEL, we use North Star Imaging X5000 X-ray machine, and it has the capability to view the radiograph in real time. So it means that in real time, we can also set the parameters of this X-ray so that we can highlight the region of interests. These parameters can also be saved so that we can use them for future analysis of similar samples. And that would be it for our short discussion on digital radiography.
Okay, learning from the principles of X-ray and digital radiography, we come now to the computed tomography. Computed tomography, or CT, is an enhanced application of digital radiography. Image of sections of objects produced by a penetrating wave. The X-ray must be stronger enough to penetrate through the whole sample. Widely known in its application, In medicine, where the X-ray source and detectors rotate around the sample to obtain the image of the multiple angle. Using the processing software, the radiographs are reconstructed into cross-sectional image and turned into a 3D virtual volume. In terms of its features, for example, we can view internal features of an object without physically destroying it or cutting through it. We can analyze the depth of the features unlike in radiographs. We can analyze materials differences based on density variation, for example, the gray values or the difference in color and intensity in the 3D volume. Next is a very effective non-destructive test with no significant alteration for succeeding tests. So initially, we can do a non-destructive test before we go through a destructive test. Okay, so in 3D CT X-ray, scanning has limitation. Number one is sample thickness. So sample thickness can vary also in types of material. For example, the limitation of our machine is or has a limitation of 2 inches of steel and 8 inches of aluminum. When we say sample thickness, it will vary in terms of how thin or how thick is your samples or how the X-ray will penetrate your samples. In types of material, primarily for metals or high density materials has a limitation as I told you about steel. But in terms of low density materials like aluminum and plastics, we have a downside in terms of viewing the samples. In terms of 3D CT X-ray, the scan duration is much more longer than a standard DR or digital radiography. Introducing the newer and latest equipment in ADMATEL. This is the 3D CT X-ray X5000 manufactured by North Star Imaging. Our NSI X5000 industrial capabilities. It can fit samples from 121 centimeters in height and a diameter of 81 centimeters. We can have a real-time viewing of sample while setting up the parameters. The parameters are saved for future analysis of similar samples. We have specialized settings and types of scan that accommodates various types of samples. Using our 3D CT X-ray, we can do different types of scan, like vortex, mosaics, and subpix. These are proprietary algorithms by North Star Imaging. Vortex. The detector and the source move vertically while the sample is rotating. While in mosaic, this is scanning big or small samples in detail in which the detector moves along the sample while rotating. Then the software stitches the scan data into one. In subpix, it is a technique in which the detectors move half a pixel to generate a much more higher resolution of scan. Three-D volume reconstruction. It allows virtual cross-sectioning of the samples in which is generated by digital radiography. Also subject to digital magnification, relying on its resolution measured in voxels. The smallest measurable interval in voxels expressed in microns per voxel. So in terms of pixel, we are viewing the image in 2D, while in voxel, we are viewing the image in 3D, and we are expecting to have X, Y, Z planes. In terms of our services, we can do analysis in terms of these following capabilities. Number one is high resolution rendering. So in terms, we produce 3D volumes, we export it as either an exe file, an autorend file, a video file, and also an image, depending on the customer needs. We can do 2D and 3D measurements of your sample. In terms, we can do what they call coordinate measurements. If you have a 3D drawing, we can compare it to the actual scans. Meanwhile, in terms of comparative analysis, two different scans, for example, a bad one and a good one, can be compared as similar to the 3D CAD comparative analysis. Void analysis, in terms of doing virtual analysis and measurements, we can measure the voids in terms of its volume and somewhat a particle analysis of the void. Lastly is we can do a wall thickness analysis relative to the outmost thickness of your sample. Virtually, we can also determine this using a 3D comparative analysis with your CAD drawing. So learning from DR or digital radiography and CT or computed tomography, here are some applications that we did. For the semiconductor, this is an example of an integrated circuit. Next is an electronic device. For example, is this camera lens. For medical applications, this is an example of 12-year-old skull. And next one is a knee replacement femoral component for biomedical applications. So in terms of defense, military, we can do a quality check on a handgun. This is a 9mm handgun. While in terms of plastics, this is an example of multi-component water filter cartridge. For concretes, this is an example of composite concretes. For battery application, this is an example of a power bank. For research and development, PNRI or the Philippine Nuclear Research Institute with Dr. Angel and his team studied coral bonds using X-ray. In partnership with ADMATEL, we can do a 3D CT X-ray of the sample and produce a coral map. The map or the bonds that you see in the image represents changes in sea surface temperature. Another one is from the archaeological studies of the University of the Philippines by Dr. Mijares and his team. excavated the tooth from a dig site in Bulacan. As the research goes, the scan of the tooth can generate information such as diets of prehistoric people. Can you imagine if we collected not only a tooth but a teeth? We can gather much more information about it. In addition, this is a marketing and product development coming from ITDI or the Industrial Technology Development Institute. So here is an example of the ITDI's Abaca reinforced composite from the Material Science Division. As you can see, we can now see the Abaca fibers without even cutting the sample. Another one is the ITDI ready to eat pack of hope. This is from the Packaging Technology Division. Next one is the ITDI's Carrageenan capsule from the Chemical and Energy Division. For the next segment of this webinar, we have this bonus tutorial for the EFXCT application. You may opt to download the file under the link below, and please take note of the system requirements. It doesn't matter if you haven't downloaded the file, you may opt to download this after this webinar. Okay, welcome to the second part of the webinar. Basically, this is a demo and also a tutorial on how to control, manipulate, or run the application of an EFXCT Lite. Basically, this application is the 3D volume on which generated to the 3D CT X-ray in our laboratory. So once you avail our services like the 3D CT X-ray, you will be given this kind of file. So on my desktop, you will see this icon. This is the actual auto-run file. So basically, this is a compressed file in which the 3D volume is imported. So on the file, you will see the file name. So basically, I will explain later on what will be the scan sample that we ran for this tutorial. So you will see the file name, the voxel size, and what bit it was exported. Okay, so you will learn what is EFXCT. So what is the environment of the software, how to control the histogram, the basic controls, what is the planes, and how do we measure using this, and how to capture image and videos, and how to export the file. Okay, so we double click the icon. So this will pop up. Reload. Okay. So when opening the CT file, you will encounter two windows. One is this one, the main view, and this one. This one is a quick start window in which a basic tutorial on how you will manipulate this software. So basically what will I teach to you is basically the content of this quick start. Okay, so if you want to go back to this quick start, you just click the about and show quick start. Okay, but for now we have to close this. Okay, so this is a 3D CT scan of a bullet. Actually, it's a 9.5 millimeter bullet, as you can see. Okay, so in this window, you will see the view of your 3D scan on the center, and then there are icons on the left. So basically, the icons represent this. So topmost is histogram, the export slices, the isosurface, and the snapshot. On top is the file and the view. Okay, so at first, well, this is already processed volume, so you can already see the cross section of the bullet and also the actual view of the bullet. But normally, the volume will be in a grayscale value. So I'll just repeat this one. So you click histogram, and then you see this window, the histogram. Okay. So we'll click the gray value here. So then you click reset. So the histogram represents gray values. Okay. So the lighter the value, it will be the highest density, and the lowest value will be the lowest density. So if we put the mouse, hover the mouse on this window, you will see this kind of cursor. So the four-sided cursor. So this four-sided cursor can move this what we call keys. Okay. So let's try. So we click this one, then move either to the left and to the right. As you can see, something happens in the volume. So this keys represents colors, in which also represents the density, which also represent the material. Okay, so as we go on, we'll be dealing this much more and try to hang in there in controlling the histogram. Okay, so going back, so put your cursor on top of the key, then left click, then scroll. This will all narrow down the other keys. Now, narrowing down the other keys will give you different or changes in what you will see on the volume. Okay, so as you can see, we can see different specifications and materials present on the volume. Okay, so as of now, you can just play around and move the keys. Okay, so moving forward, using this, you can change the color. For example, this represent gradients that represent again densities and gray values. Okay, so you can click this one, changes, and this one. Okay, so actually in different densities, you can also change the opacity. For example, if you choose one of these keys, you will have this kind of cursor, and then you have this small key in which it can only be changed vertically. So when you change it, it will change the opacity of your color. So basically it represents the violet color or the purple one. So it will be changed in its opacity. Okay. So moving forward, let's go back to the gray values or gray settings. Okay. So Yes. So these green lines represent the bounding box. So if you press the space bar, you will now move on the plane. So normally when you open this file, it's already pre-capped on this plane. So if you can press the space bar, you will go back to the bounding box. Okay? So don't be afraid. You can do it over and over again. So this file will not be saved as the way it is been given to you. So you cannot do any harm with this with this volume again, or with this sample. Okay. So again, click on the spacebar, then we go to the bounding box. Okay. So pressing keys like X, you will be given the view of the X plane. When you press the Y key, you will be given or viewing the Y plane, and you press the Z, you'll be given the Z plane. Okay, so basically it's the most common controls that you can get, but typically we are a mouse person, so we can just move the mouse either from the left to right. So you will move the volume and right to left and up and down. Okay. When you want to zoom, you just have to scroll and you will zoom in and you will have to zoom out. Okay. So going back, so this volume can be cut or virtually cross section. Okay. So when you cross section the volume, the keys needed to be pressed is from the numbers 1 to 6. So each number represents a plane. So for example, or every time that you will be given this file, the cross section or the default cross section will be number 1. So we press the key number 1, and then your sample become uncut. Okay, now you can press the key 1, and then you view your first plane. So it will generally be the same with the other numbers like 2 and 3. So 1, 2, and 3 represents X, Y, and Z planes. So relatively from 4, 5, and 6 is just the negative value of that plane. So if you press 4, 5, and 6, okay? So don't be confused. When you press again the numbers, the plane will be removed again. So press 6, press 5, again, press 4, press 3, press 2, and press 1. Okay, so each plane represents a color. So for plane 1, it's green, plane 2, it's yellow, plane 3, it's red, plane 4, it's blue, plane 5 is pink, and plane 6 is violet. So you can change it, but the default will be that way. Okay, so moving forward, so if we right click, we can see these options like surface, define center, or the camera center of rotation. So we can do this one. So we can take this one, and then that will be your center of rotation. So basically, if you move that one, that will be your center of rotation. Okay. So next would be volume, planes, or clip planes, your display. So from display, you can see this outline, selected outlines, background. So from the essence of time, I will not explain this truly, but you can explore it. So video snap dialog, toolbar, and save appearance. Okay. So basically, this is the right click actions or options. So moving forward, we'll do the plane window. Okay, so again, we press 1. So we'll have this plane. Okay, so a little trick, if you want to rotate, so if you want to rotate the view, you just have to move on the bounding box by pressing again the space bar, and then press Alt, then create an arc or an angle to re-angle your sample. Okay, so it's similar with plane. So if you have mistaken to rotate the plane, you just have to double click again. So when you double click, it will return to the previous view. Okay, so picking out the one plane, again you press 1, then right click you to click plane 1, then show 2D. So when you show 2D, a window will pop up. So this window will represent the actual DR of the plane 1. So from this, the views are this scroll bar, in which when you scroll, it will scroll the cross section, okay, from up and going to the bottom. Okay, the arrows on the scroll bar will define the cross sectioning. When we say define, it will be a much more refined scrolling in terms of cross sectioning. So you can press it, a much more slower cross section and define. Also the same on below. Okay, so when you right click, you can find the measuring tools. You have the length, the diameter, the angle, the arc length, circle gauge, the text, arrow, ellipse, and polyline. So basically, again, the essence of time will just do the length. So doing the length, you just have to click this and you will have your measurements. Okay, so again, may I remind that this will not save in terms of what you are viewing now, but in terms of viewing or getting save image is by doing a snap. Okay, so there is a difference between snapping this plane and also snapping this 3D volume. So in terms of snapping this 2D volume, you just have to right click, then go to video and snap, then takes a snapshot. Okay, okay, so don't you worry, there's something happened, but we'll explain it later. But in terms of finding where the image will go, so you have to right click, go to video and snap, and then go to video and snap dialog. Okay, so from here you can do, you can, sorry, you can record a video or take a snapshot. So where you can find the save file is in here. You have to click this, okay, and then you will find this images. Okay, normally it will be, the folder of screenshot will be together with the actual file. Okay, so I have previous images that I have already taken. So going back, so we have to close this, and doing snapshots is also the same in the 3D view. So this 3D view, you can also do video capture and snapping down on the 3D volume. Okay, so I will not explain it further, but this is quite very easy to do, and maybe uh, quite a thing on doing this 3D volume and doing the analysis. Okay, so next on the button is the export. So the export or the quick export, I will not do it in the essence of time. So what is the cross section plane that you have, it will export how many slices that it will take. So for example, if you have this plane 1, it will export the whole image or stock image of the cross section of the plane 1. Okay, so lastly, we'll have the isosurface. So when doing the isosurface, it is relatively doing your sample or solidifying your sample, but on a surface scale. What I mean is that using the ISO value, you are solidifying your generated 3D volume, but in a sense, the surface. Okay, so to make it faster, you just unclick the show, so it will much more do it faster. Okay, so so in terms of this, why maybe you're wondering why do we have to solidify this sample? So basically, as you can see here, this produces triangles, and if you zoom in, so below when zooming in, hope it works. Okay, so again, uh, I will click wireframe and remove the. Okay, so basically, as you can see, there are mm, thousands and millions of triangles in which these are very relevant to people like doing AutoCAD and doing 3D printing. Okay, so as I mentioned, 3D printing. So in not in this file, but in our laboratory in the actual CT, effect CT, we can export the file into STL file. So basically, when we export the file into STL file, you can 3D print what you exported in terms of what you scan. Okay, so basically, this is one of the features of the effect CT. Okay, so I think I captured everything, and okay, so I hope you enjoy this short tutorial. If you have any question, you can comment down. And if you have any further questions or refined questions, you can email us. Okay, so this will be the end of my tutorial. So hold on, there will be a question and answers. And I hope you enjoy this tutorial. And again, thank you very much for engaging into our webinar. So, thank you very much for attending our webinar. So, again, this is brought to you by the Advanced Device and Materials Testing Laboratory by the Department of Science and Technology, Industrial Technology Development Institute. If you have any questions, please kindly leave your comments here and we'll try to answer it as soon as possible. But if you want to more refine your questions, you can email us at services@admatel.com or visit our website at www.admatel.com. Again, thank you very much and good day.